Hi, I'm Ahmed Dawood, and in this session, it will be a continuation of our last session, which was uh, about the case study. So here we will do model building. Okay, the above part till the idea we already have done in the last session. So in this session we will do model building. And keep in mind here we it's a regression problem, so we will use some regression model like a linear regression or polynomial regression. Okay. So first of all, we have our data uh, that we already have, and we will split our data into x and y, which will be independent variables and dependent variable x and y. Okay. After that, we have about four columns that are still categorical columns. Uh, like here, if you know, these are the studio primary, season of release, media type, and one another column also. We have four columns here that are categorical columns, and we have to convert that categorical columns into some numerical column by using get dummies. Okay, we want to do some uh, we want to get some dummy variables in which all the category if one column has five categories, categorical column have five categories, so it will create in some cases when we are doing one hot recording, but it may generate five columns, but in case of get the miss it will generate four columns accordingly, and in each column it will present the value in the form of binary value 0 1. Okay, and there is also a reason why it convert into, instead of five categories it convert into four columns. The reason is that if the particular category, let's say here, mm, yeah, we can consider that season of release. Season of release have four seasons and one have is missing. There are total five categories in that: spring, summer, winter, fall, and missing. Okay, but it has converted into four columns. It means that when there will be a value which will be considered as a fall, then all that four columns will have zero value. In that case, maybe here, yeah, this one. 0 0 0 0, it means that it is not belong to missing, not belong to winter, not belong to summer, not belong to spring, then it should be belong to the fall. Okay, in this way it convert. Okay, so we are here converting our categorical columns into numerical columns, and here passing like x, which is our independent variables, and columns is equal x dot select type I. We are going to select the columns that are object or categorical columns. That obviously there are just four columns. I think we should re consider here like media type. If I will media type, season of release, studio primary. How many columns we were having as categorical? Studio, season, ongoing. Okay, ongoing is that Boolean, so it can be the form of 1 0. Generally, we have three columns, three categorical columns, and it will be converting into dummy columns. Okay, or you can say one word encoding, in other words. So here we have converted our categorical columns into numerical columns. Now we have X, and here you can see that all the columns, tag columns, are already in the form of binary. And here in the case of like media type, also converted into the uh, dummy variables in the, or you can say binary columns. And season of release is also converted. Studio also converted here. Yeah, all the remaining are studios. And row first is equal to true means that the categorical column that originally our X have, it should drop. Okay, because now we are going towards the part of model. Now we have 70 columns and 12,000 rows. And now I am going to submit my data into training dataset and testing dataset by using train test split with the ratio 0.3. Test size means 30% should be test um, of 30% of original data should be a testing dataset, and remaining 70% should be of training dataset. Here you can say the number of rows in training dataset are 8400 and number of rows in the test dataset are 3600. I am going to fitting a linear model, which is a linear regression, and here I am going to fit means I am going to train my model on that training data. Now I want to explore my coefficients. Okay, here I am just I have a simple you can say data frame I am creating here to visualize more clearly. Here the data frame, and here I am appending of coefficients, and at the end of the coefficients there will be a you can say intercept in the form of a number, and second index will be all the names of the columns, and columns just one column coefficients. Here you can see these are the episode, duration, ongoing, and in this way all the columns have some coefficient, and the last one will be intercept. Intercept have a it's a 2.8 value. Now here the point is to consider here. You remember in the part of visualization, if we were when we are discussing when we have to um, find a relation between multiple variables, and we want to do analysis on multiple variables at a time, we can also use linear regression for that purpose. Okay, means target column or the column that we want to see the relation with that column, it should be y, and other all the columns can be x. Okay, so what is the how we can do that? It means like here the equation will be like these are the coefficients. The equation will be target which is a rating is equal to minus 0.000205 into episodes plus 0.003 into duration plus 0.38 into ongoing up to so on plus intercept. In this way our equation of model after training will become. Now here some coefficients have negative signs, some coefficients have positive signs. It means with the increase of that value, with the increase of episodes, our rating will decrease. This negative is shown. And as this has a very less strength, 0.000205, it means that episodes have a very less relation with the linear relation with the our target column, which is rating. Okay. So we have some of the negative like these studios collaboration is also negative. Content warning has a negative coefficient. Drop also have negative. And if I will show you here where I have written all of them. Coefficients of episode, duration, years running, ongoing, and some of the tag columns. All the season of release columns except the summer. Some of the studio columns are positive. Uh, how they are positive? Episodes are negative. It should be negative. Yeah, episode should not be here. Duration should be here. Yeah, it's a by mistake. Yeah, okay. Okay, duration, years running, duration, years running, and what is the next? Ongoing, and some of the tag columns, and these columns have positive coefficients. It means that increase in these values, increasing in the values of these column will lead to increase in the rating of an anime. And coefficients of episode content warning, vast drop, some of tag columns, media type columns, and some of the studio columns are active. Means increasing in the value of these columns will lead to a decrease in the rating of an anime. Okay, in this way you can interpret your coefficients for the sake of analysis. Okay, multivariate analysis. Okay, so till now we have trained our model. Now we can evaluate our model on our testing data set, and also we can evaluate on our training data set by using the evaluation measures. We have learned regression measures in our uh, throughout that module. Um, like a mean square error, root mean square error, R square, adjusted R square, a lot of measures, about 5 to 6 measures we have learned. Okay, we will create a function here in which all the 5 measures we will pass just our model. If I will show you our function here, yes, we will pass our model, our predictors means independent variables, and in our case here you can say X test and target Y test. Model X test Y test, model that is already trained, and this function will evaluate and all the measures here, okay, and calculate all the 4 to 5 measures we will see uh, in the value. This function will calculate. Okay, now we will use here 1, 2, 3, 4, 5 measures we will use here. Root mean square error, mean absolute error, R square, adjusted R square. Okay. Uh, these RMSC, MAER square can be used from the scalar. Okay. Uh, and for the R square and map, map is something new for you. This will be for that we will create two functions, adjusted R square and map score. Now, as map is new for you, so I am going to elaborate here what is map. Map is nothing, it's a mean absolute percentage error. By the formula, you can get an idea. When you have two columns, when you are going to evaluate your regression model, you will have two columns. One column which is predictions of by the model, you will pass in inputs or independent variables, values of independent variable to your model, and model give you some prediction. You will save all the predictions again in the one column, and the column that you originally have which was having true values. Okay, you usually have two columns. One is usually you can say predictions, and one is targets, okay, or true values. Now, the difference between prediction and target value is we usually call as error or residue. Okay. Now, the difference between the target and the prediction, uh, if we will represent in the form of percentage, then we can say it's a mean absolute percentage error. How we can represent? Here you can say the difference between target and prediction and take an absolute. Difference between target and prediction, take an absolute, and then divide by target value, which is a true value. Means true value minus prediction, take absolute, divide by true value, it will give you a percentage. Okay. Now you will take a mean of all the percentage of your data. Okay, like you have two columns, and if you will calculate a 1% against like a one true value and prediction, and in this way you will calculate as number of percentage as number of prediction and true values you have. Okay, you will calculate a number of percentage, and then you will take an average of all the percentage to represent for just one number. Okay, here you will take a mean. Here you can see you will calculate a mean. Sorry, this one, and then you will multiply it by 100 to present in the form of percentage. Okay, it's a 17%, 18%, 19%. Okay, what it map represent, that how far your predictions are from your true values in the form of percentage. Like your true value or your prediction is 17%, like let's say 17% is away from your true value. Okay, you can represent your error in the form of percentage. It's a map score. Just it as square, R2 score is already you are familiar with that. Okay, so you know what adjusted R2 score here, the values will be passed here, and it will calculate the by using that formula. Map score will calculate by this formula. Now here in the model performance regression, there are three model and independent variables, and dependent variable will be passed here, and all the scores are calculated here, and then it will be present in the form of data frame. Now we will see like this training performance. We will first test our model on our training data set. Okay, model performance regression. This is this one function. We will pass our linear regression model that we have trained extract independent training data set and dependent target column of our training data set. We have passed here and model giving us a performance like here you can see adjusted R square is 0.53. It means your model is explaining 53% variation of your target column, or you can say your model has is, in other words you can say it's a giving 53 score, 53% score, you can say 53% it's a good, or you can say in other word the variation uh, in your target column, or explained by your 50%, 53% variation of your target column is explained by that model, which is not good. It should be high, but it's not good. And what map is representing, it means that if you will predict some value by your model, it will be have 17% error with your true value, okay, on average. Here R square and adjusted R square, same sort of, both have explanation. And in the case of adjusted R square, it means, I will elaborate uh, in the session of measures that adjusted R square also get the irrelevant features also. Mean absolute error, it means that if you will predict some rating, like the rating is in the form of like from 0 to 5. If you have rating 4.5, the model predict 4.5 rating for some sample, then it can have 0.45 error. Okay, it means that if you are predicting 4.5, then it will be in the range of 4.1 to 4.9. Okay, it will not exactly the 4.5. And the root mean square, it means it has 0.56. uh, so still here we can say that our model is not so good. Okay, and there can be multiple reasons. One reason can be that your target column, your independent columns cannot represent your target column, have not good relation with the target column, you can say. And secondly, you can say your independent columns have some non-linear relation with your target column, but our model is here linear, so it has not captured the patterns from the non-linear independent variables. Okay. Anyways, here test performance you can see here is almost same as just a little bit less than the training performance. Okay. Like adjusted as well 0.50, but in the case of training data set it's 0.53. We can say that our model is not overfitting, because in case of overfitting, it will have high score on training data set but low score on test data set. But here both have similar type of scores, so we cannot say that our model is overfitting. Instead, we can say model is underfitting here. It's not giving a good score on both data sets. Gradient test R square are 0.5351, indicating the model explains 53% and 51% of the total variation in train and test sets respectively. Also, both set scores are comparable. Okay, there can be another reason that I forget here. I forgot. The reason can be that we are here using a skewed, some like I told you that some columns are very have right skewness in them, so we have not removed the skewness before training our model. There can be this can be a reason. So when we have seen our model is here performance page showing that our model is not so good. So here I am going to transform my non-binary independent variables, okay, which is not binary, to remove skewness, because we usually have skewness in numerical columns. Binary columns, it's just a numerical representation of categorical columns. Okay, so we have to transform our non-binary independent variables. Okay, to fetch the names of non-binary, I am here like running a loop, and appending all the non-binary columns in the non-binary list. And here I am printing these six, seven columns I have here that are non-binary columns. Okay, and all columns have high skewness, and all the columns have right skewness. So by using power transformer, I am going to transform uh, my non-binary columns, remove the skewness, and here I have transformed that. Okay, by using fit transform. Now I will train our model on transform data points. As I told you, I have not transformed my binary columns. I am just transforming my non-binary columns. The reason I told you that non-binary columns are numerical columns, and binary columns are actually numerical representation of categorical columns. Okay, so we don't need to, because, and also there is a reason that it has just two categories. Binary columns has just two categories, 0 and 1. So there can be a chance that zero can one of the category in between 0 and 1 can be very high and one category can be very low, but we cannot scale in the transform in the way of transformation or to remove the skewness, because these are the categorical columns. Here we have passing a transform training. Now transform training data, and now we will train our model on the uh, you can say norm or less skewed data. Okay. Okay, you can also explore the coefficients again, but no need here. We will directly jump on the performance. What is the performance of our model when we have trained our model on the less skewed data? Now here you can see a lot of difference in is here you can see that we have just um, removed the skewness of that seven columns, but our accuracy is improved like from 0.53 to 0.67, about 14% our accuracy has been increased here. Okay, so you can also got an idea how much linear model is sensitive to the skewness of the data. Okay, so here the score is 0.67 and errors are also decreased here. Even in the case of testing data set, it's also 0.64. As compared to training performance, it's low, but again quite good as compared to model trained on non-transformed data. Okay, so as I told you, we have two key questions. One question is to have such a model that can predict the rating, and the second was that to find the important features or important factors that are influencing that influence usually influence the rating of an anime. For that, I am going to use forward feature selection using sequential feature selector. What it will do, we will see the advantage of that, how it will do, and what is it. Okay, so how to select a subset of, okay, so here the purpose of using that forward feature selection is to select a subset of important features. Like here we were having 70 independent variables. If I will show you here, in the case of X train, I trained, here you can see we have 70 independent variables. Okay, so to select a subset of important features out of like a 70 features with forward feature selection using sequential feature selector. Why should we do feature selection? The reason is that one reason is it reduce dimensionality. When it reduce dimensionality, it now the training process also speed up, testing process is also speed up, your computation also decreased. These are also the advantages, and other advantages, it discards deceptive features, which are features that are irrelevant and which are just you can say not giving any advantage or not expanding the target variable, just wasteful features here. It discards that deceptive features. How it works? Okay, it starts with an empty model and adds variable one by one. Okay, it will have empty model. Then it will train a model on just one independent variable. Okay, one dependent variable is always one dependent variable, and it will train instead of 70 independent variables, it will train model on one independent variable, and then it will give us model will be evaluated and it will give some score. Then the model will be evaluated on model will be trained on two independent variables, and in this way model will until we reach our specified number of important features, it will keep on training. Like a first model will train on one independent variable and give some score, then two independent variable give some score, three independent variable give some score, and in this way so on. Okay, now when the case of one independent, it will train on one independent variable. It will first, in the first case, it will uh, uh, it will train on the one independent variable, which is most important independent variable. How it judge that this independent variable is most important? It will train split our data set independent variables. Like we have 70 independent variables, it will split our 70 independent variables into 70 parts. Okay, each independent variable will be considered a separate part. Then it will train the model on each 70 parts, and which feature or which column will give a good score. This will be our considered as the most important independent feature in the first iteration. In the second way, second iteration, the same process will carry out. Then we have already selected, and one column will attach one by one, and which column will give good score among of all of them will be selected as second important feature. In this way, model will select first, second, third, fourth important features. Okay, so that's why it usually called forward feature selection. And here I am going to use. You can also implement that by using sklearn, but here I am using the extension machine learning extension dot feature selection, and here I am importing sequential feature selector. Okay, and this is API for that. Okay, you can read the parameters also here. Sequential feature selector, the popular forward and backward feature selection operator. Okay, from the machine learning extension. Okay, come back. So you can install that pip install mlx extend, and after installing you can import sequential feature selector, and then you can use that. Okay. Okay. So I'll give you the more clear uh, understanding of forward feature selection that I am discussing here, uh, that we are going to use to fetch, or you can say to extract some important features. So how it actually works, you can also read this documentation of that sequential feature selector from provided by the machine learning extension. So anyhow, I will explain you how forward feature selection works. Let's say you have here, this is your data set in which you have, let's say 1, 2, 3 up to, you have 70 independent variables like we have here, and you have just one. Let's say I will move from here. You have just one dependent variable, or you can say target call. Okay, what you will do in first iteration, you will split like this 70 independent variables into 70 columns. Okay, like separate, you will make 70 columns separately. Okay, like this is one, this is two, up to the 70. This is feature number one, feature number two, this is the feature number two. Okay, this is feature number two, this is the feature number 70. What you will do now, forward feature selector will do here. Here you will have a model. If I will make it small, okay. So you will have a model here. You will pass this like a feature number one here. Uh, Instead, if I will make here, let's say, here I can pass. Okay, you will have a model, and now you will feed this feature number one, and from here you will feed that one dependent variable. Okay, and this model will give you some score. Okay, you can say this is score number one. Okay, you will feed feature number one, and of course a dependent variable also, and just one independent variable, feature number one, and it will give you some score. In the same way, now you will train a model on feature number two, and it will give you some score. Okay, keep in mind, independent variable are always you have to feed during the training, so that's why I am not always mentioning here. uh, in this way you will train all the you will train model uh, separately on all 70 features, and all 70 after training you will get some score, like score number 70. Now which feature is giving highest score? Let's say which feature is giving highest or maximum score. It will be your first most important feature. Okay, it will become first most important feature. Okay, let's say your feature number uh, 9 is giving highest score in the first iteration. Now you have selected one feature. Now second times, instead of this second time you will have this type of data sets like 1, 2, and up to this. Okay, and here you have my like what feature number 9 is. This will be your feature number 9. This will be feature number 9, and this will be your feature number 9. It will be fixed here, and now you will have here accordingly this will be feature number 1, 2, and up, so 70. Okay, now again you will train your model on these data sets in which the two features, one feature is already selected, and again which data set will give you a good maximum score will be selected at the feature will be selected at your max most important, second most important feature, and in this way so on up to the end, and up to the part up to the features that you have mentioned in your parameters. Okay, you got an idea how it works actually. Okay, so forward feature selection, you will evaluate each feature one by one, and you will on the basis of highest score you will select the important feature. Now come back here. Okay, so here you are importing for sequential feature selector here, and regression linear regression you are using as a model. Now you have created an instance of your SFS, in which you are passing you the first parameter regression. Second, here you can mention how many important features, first like first 30 important features, for first 40 important features, how many important features you want to extract. You can mention here, and first I am mentioning here that I want 70 all the important features. Okay, yeah. So format, if I will make true, it will be uh, we follow the forward method that I have shown you here. Okay, this forward method, it will start from the 0, it will start from the, or you can say start from the 1, and like here you can say it starts with the empty model and adds variable one by one. Okay, in each forward step you add one variable that gives the highest improvement to your model. In this way, if you will make here false, it will follow the backward method, and you can also study backward method, what is backward method from here, and also they have given a very good tutorials as you can also see. Okay, from the documentation. Machine learning um, extend here. You can say you can also write machine learning extension, sequential feature selector on the Google, and you will get that documentation. Okay. Anyhow, then you will pass a floating. No worry about that uh, parameter. And if you want to read, you can uh, read all the parameters from these documentations. Okay. This is API. Yeah. Okay. Come back to scoring. Which score you want? Like each time you have to evaluate your model. Like this is the score. Score one, score two, score three, and which score you want to use. You can mention here. Like here, I have mentioned R2 score. N jobs is equal to minus one. It usually that when you have to run that algorithm or that module or that function, uh, how many processors you want to use your of it. It's a hardware related. If you will mention minus one, it means all the processors or cores of your computer will be used. Verbose is equal to 2. It means verbosity. How it will when you will run, it will give you all the detail. How much detail you want. Like here it has mentioned a feature. One feature is used as a independent variable, and it is given 0.49 score, and now two features are using here, and all the details, how many time takes, and how many iterations, all this stuff. For that, usually verbose is usually used and also mentioned in a lot of documentations in the sklearn also. CV is equal to 5. I think you have not learned that till now. Cross validation, it's a way of splitting. Like we usually split our data set into training and testing. We train our model on training data points and test or evaluate our model on the test data points. Okay. But cross validation is something different. Like here, if I will mention CV is equal to 5, it means you will split your data into 5 parts. 4 parts will be used as a training data points, and fifth part will be used as the test data points in first iteration. Second time, the part that like a fifth part, fourth part will be used as a testing data set. Third time, another part will be used as the testing data points. In this, if 5 times different testing data points will be used, and 5 scores you will get, and average of that scores you will calculate. In this way, cross validation work, and you can explore and learn it by searching. Okay, it's very easy. Okay. Okay. Now I am going to train my model. Sorry, train my this SFS dot fit extend transform. I am passing a transform my independent variables and by train. Now, to save the time, I already have run here. Okay, after running, when I will plot by using machine learning extraction dot plotting, and here I am importing plot sequential feature selection as a SF plot SFS, and when I will plot that, okay, you can use here figure one plot underscore SFS, and here you can pass SFS, which was your sequential forward selector dot get metric dictionary, and kind standard error or standard deviation. Okay, you can pass here, and you can get that type of visualization how the score is improving. Okay, instead of reading here one by one, you can see all the score visually, and you can here see when there is just one variable, the score was 0.45, and when there are two features, score increased to 0.5, and in this way, as features are increasing, score is increasing. And you have seen after 30 or 32 features, score is not much increasing with the increase of features. Okay, remains almost constant here. Okay, so here I have decided that instead of all using 70 features, we can use the first 32 important features, most important features here. Okay, so here the regression model, and instead of passing like first time I have mentioned here all the 70 features, Here I have mentioned k features is equal 32. Okay, now I am trying to fetch the first 32 important features. I have again run that same SFS module. I have trained on that. Now, by using the attribute of SFS dot k feature underscore index IDX, I have extracted the feature numbers, okay, feature indexes which are more important, most important. 0, 1, 3, 5, 6. It has selected that these features are most important. And you can also tell you to your team that uh, according to me, these features or these factors, okay, you can say these factors most influence the rating of the enemy. Okay, and here you can see that we are going towards the second one question of our key questions that to answer one of the question of our key question, which was what are the key features or what are the factors that influence the rating of the enemy. You can say that these, okay, you can by passing to that into the columns, you can say that these columns, these are the most important factors that influence your rating of the enemy. Okay, I have passed these feature columns in here, and I have extracted the against the indexes. I have extracted the column names. Now we will fit our model. Instead of 70 features, I will fit the model on the just these 32 features. Okay. Now I will have another explain final in which I will have 30 columns instead of all the columns. Okay. Okay. Now I have trained the model, and here all the coefficients are in below. Now again I am interested in the score. The score for the training performance is 0.67 and for the testing performance is 0.64. Score is matching, score is not significantly increased here. But here you can say that when you are before you were using 30 70 independent variables, here you are using 32 independent variables. Now your training performance will be increased, your computation decrease, your time will be saved, your speed will be increased. Okay, so you are not getting edge regarding the performance measure, but you are getting edge, you are getting advantage regarding the computation, regarding the time, or uh, you can say regarding the other aspects. Okay, okay, so this is one of question we have answered here, that these are the important features according to us. We can tell to our company that these are the important factors that influence our the rating of an enemy. Okay, so now second part, till now we are figuring out which model will be good for the like a good predictive model that we can give to our company to predict about the rating of an anime. So here, instead of just linear model, I am going to use a polynomial regression model. So, for the polynomial regression, you have to first convert your features into some polynomial features by specifying some degree, and then you have to train the model. Okay, so instead of getting the transformed 32 important features, I am trying to extract the 32 important independent variables without transformation. Okay, because I want like these previously variables are already transformed. Okay, you remember. Now I am not interested in the transformation before the polynomial regression. I have to first convert my columns into polynomial features, then I will do transformation, and after that I will feed to the model. Okay, I have here have these independent variables in which I have columns without transformation. Again, polynomial features will not have any effect when we will have binary features. Okay, 1 0. It can have effect on the numerical features. So that's why I am here separating getting the features or columns names that are non-binary, and here the list of the columns that are binary by running the loops. Okay, now I have converted using polynomial features. I have converted the model my non-binary columns into degree 3 polynomial features, in which these columns will be converted into, like, we instead of just, if we have like 12 columns, we have about 20 columns here. Instead of 20, about we have 30 columns will be here. Okay, if we are here, we are passing just 12 columns, then you can calculate by the formula, and you can also manually calculate here, like this number of columns we will have now. Okay, instead of these non-binary columns. Okay, now upon that non-binary columns, when you have skewed data already, and you have applied you have taken the power on that, your skewness will more increase here. Okay, now to remove this skewness, I have used a power transformer, and then I am going to feed first. Okay, so I have my data here, 32 independent features without any transformation. Then I have separated my 32 independent variables into um, like non-binary independent variables and binary independent variables. Then I have applied polynomial features on non-binary independent variables, and after that I have applied power transformer on the non-binary independent polynomial features. Okay, after power transformation, I am now going to concatenate my non-binary independent transformed features with the binary independent features. Okay, maybe you get confused. You can again stop that video and go back, and again you can watch that video. I am saying that first, I have separated my known by 32 independent variables without transformation into non-binary and binary. Then I have taken a polynomial features of my non-binary independent variables. Then power transformation of non-binary polynomial features. Then I am going to concatenate my non-binary transformed independent variables with the binary independent variables. Then I will feed, here you can say I have converted my binary independent variables into numpy so that I can concatenate here. Now I am here concatenating my, this is, this is, you can say, my extract poly. This is extract poly, which is non-binary transformed independent variables, or you can say non-binary transformed polynomial features. Non-binary transformed polynomial features with the binary independent features. Okay, I am going to concatenate. Now I have extend poly here. Now I am feeding that extend poly and white red to my model linear regression. Now I will check my performance, how my performance is increased by using polynomial regression, polynomial features. Okay, you can see here that it increase like a 5% increase here from 0.7. I think here previously we have 6.7. Now it is increased to 0.72, means 5% increase in the training performance, and in the case of testing performance, in the case of R square it is 70%, and in case of adjusted R square it is 0.68. But previously what we have, yeah, it was 0.64 and it was 0.65, means 5% increase in R square and 4% is increase in the adjusted R square our performances. Now you have seen that I already have non What are the assumptions linear regression model usually have? It is sensitive to the outliers, skewness, or how it actually behave or how it actually work. As I know the behavior of the linear model, so that I have performed transformations on my independent variables, I have performed polynomial featuring be- because I have the concept of linear regression, okay, and I have increased my accuracy. From that, you can get an idea how important is it to have the concept that how the model is work, how we can increase the performance of our model. Still, our performance is not so good. If our model is predicting something, it will have 30% error. Okay, in the here you can say 40% for the new data points it will have error. If our model will predict like a 0.5, sorry, uh, if it predict 4.5 rating, then there can be a chance of 0.35 from both sides. Okay, like it can be 4.1 in originally it will have 4.1 or a 4.8. Okay, this rating, but here it is giving you the estimate that how much the people will rate within this confidence interval. Okay, now you will go towards to your like other team, maybe towards your CEO or your managerial decision maker team, that I have designed or built a model that can predict the rating with that much error, or you can say with that score. Okay, or my model will give you the 70% score, 70% accuracy. Can it be good for you to deploy? They will say that, okay, so we should have some more accurate model. Then you will ask that, okay, so according to these data points, according to these columns that you have given me, the data, um, there is maximum chance that we can achieve this much accuracy. If we want to increase the accuracy, uh, we should have some more columns that can have a good correlation with our target column. You will go towards the data engineer, you will say that either we can get more columns so that we can increase our models accuracy, models performance, and maybe you have to go back towards the pre-processing part and you have to apply some different techniques to filling garbage values, filling missing values. Okay, in this way the data science project will iterate until we will get our optimal solution. Okay, but here for the sake of regression problem, you got an idea how we can tweak our regression model, linear model, to get our desired performance or desired result. Okay, now till here maybe we can if we will make change in the pre-processing part that we have not done in that session, but maybe with changing some different techniques, we will get more score. Okay, but if we want significant increase in score, then we have to add such a columns in our data that can have a good correlation with our target goal. Okay, I hope you got a lot from here. How the data science project work, how the regression problem presented to our data scientist in a company or in a field, how he tackled the problem of a regression problem, how he follow the pattern, how much good concepts help him or her in designing or building a model. Okay, so for now, thank you, and we will meet in another module with some new stuff. For now, thank you.